When calculating the slope of a line, there are several methods that you can use. If you are given the graph of a line, it's probably best to locate 2 points on the line, and you can use any 2 points that are lattice points, which means that they have integer x and y values on the coordinate plane. In other words, they intersect nicely, and you're not estimating where the point is. So you could really use any of those points that I've marked. Let's say I use the y-intercept and the x-intercept to determine what my rise and run are. If I rise here 3 units and I run 6 units, that would give me a slope, often denoted with the letter m, of rise over run, 3/6, which simplifies to 1/2. Now you could also do this with 2 other points if you wish, and you will end up with the same result. Like, let's say I start at the y-intercept and I just go to this next lattice point on the line. This automatically, the smaller triangle, gets you right to a slope of 1/2. Another thing we can think about is we do not necessarily need to use the x or y intercept as one of our points. We could use any of the points that are labeled. So for instance, I could go from this point up to all the way over to this point, which would be over 4. And again, you can see that it's still going to simplify to 1/2. Notice that your line is increasing throughout, so you do end up with a positive slope. In my next example, I have a line that is decreasing throughout, which indicates I should have a negative slope or rate of change. I've labeled 2 points here on the graph. So if I do my rise over run here and I start at the y-intercept, you will notice that I'm going down and over to the right. So this will be down 1, 2, 3. So I'm going to call that -3, and to the right 1, 2, 3, 4, 5. So that will be 5, giving me a slope of -3/5. Again, rise over run. You can also determine the change in the y values over the change in the x values to get this result as well. You could also make your triangle in a different place, where you go rise up 3 units, but then when you go to the left, you would end up with a -5 there. So whether it's -3/5 or 3/-5, essentially a positive divided by a negative is going to give you a negative slope. In this example, we are given a context-based problem with a table of information. Grand Rapids Inflatable Rentals charges a setup fee and an hourly rental fee for renting one of their bounce houses. The table shows the cost of renting a bounce house for a certain number of hours. We are trying to determine the hourly rental fee for the bouncy house, and essentially this is determining the slope of a linear relationship. So our x value corresponds, or our independent variable corresponds to the time in hours, and our dependent variable corresponds to the cost in dollars. So what we want to do is figure out the change in cost over the change in time, and we want to be mindful of what our units would be here for the slope, since we have a contextual based problem. So I can start looking at the change in time, and I'm going to notice that each time I go through from one data value to another, I am adding 2 hours. Here you can see I'm increasing by 2 hours, and then you'll notice that the cost every 2 hours is increasing by $26. So every 2 hours, there is an increase in cost of $26. But if I'm trying to determine how much it costs per hour to rent the bouncy house, then I will take my change in cost, which is 26, and divide by my change in time, which is 2. And again, remember, this is dollars and this is hours. So this indicates that the hourly rental fee will be $13 per hour. And when we have context-based problems, we always want to include units.